Good evening. We are Group 39. Our topic is Deep Learning Based Framework for Network Slice Optimization in 5G Network. This project demonstrates the use of Convolutional Neural Network (CNN) to classify 5G network slices based on simulated data. The slices represent three core 5G functionalities. First is EMBB, which is Enhanced Mobile Broadband. Second is MMTC, which is Massive Machine Type Communication. Third is URLLC, Ultra Reliable Low Latency Communication. This project provides end to end functionality from synthetic data generation to visualizing model performance through multiple matrices and plot. Performance visualizations of our project includes accuracy and loss curve, confusion matrix, ROC curves for class-specific performance, pair plots with simulated resource utilization heat map. Now Pradyot will provide the demo of our project.
Okay, everyone. So I'll walk you through the code. Let me share my screen. Okay. So initially we started the deep learning based framework for network slice optimization with installing all the dependencies. So we started importing all essential libraries required for our project. Libraries like NumPy and pandas were used for data manipulation. We used matplotlib and Seaborn for visualization, and the deep learning components such as CNN layers for implemented using Keras library in TensorFlow. Finally, the scikit uh, scikit-learn library was used for pre-processing and evaluation metrics. So the first step that we did was creation of synthetic dataset. Since we didn't have access to real world 5G network dataset, we simulated synthetic data. We generated key features like latency, throughput, signal strength, user density, bandwidth, packet loss rate. Additionally, we assigned a device type like smartphone, AR, VR, or IoT, and used a rule-based logic to classify data into one of the three network slices. For example, low latency and high throughput indicate EMBB. High latency with high user density is categorized as URLLC. Other combination default to MMTC. Finally, we encoded the categorical features and prepared the data stream for the training. So the next step was to pre-process the data. So we scaled the numerical features to standardize them using a standard scaler. For the target labels, we converted them into one-hot encoded format using TensorFlow utilities. Finally, we split the data into training and testing sets, ensuring 30% of the data was reserved for testing. And next was we uh, build the CNN model. So defining and training the CNN model. So to classify the network slices, we implemented a convolutional neural network. The model architecture basically includes uh, two convolutional layers with ReLU activation for feature extraction, max pooling layers to downsample, uh, and dropout layers to prevent overfitting. So dense layer for classification with softmax activation to output the probabilities for each slice. So we use this Adam optimizer and categorical cross entropy as a loss function to train this model. Uh, we evaluated the model and uh, using the same procedure, and we got an accuracy of 90.67%. So the next step was training the model and validation metrics. So we trained the model for 20 epochs with batch size of 128. During the training, we monitored accuracy and loss for both training and validation data. This helped us ensure that model was learning effectively without overfitting.
So here we have the accuracy and loss plots from training our 5G network slicing model. On the left, the accuracy plot shows the training accuracy in blue and validation accuracy in orange. Both improve steadily with validation accuracy stabilizing around 90%. This indicates good generalization to unseen data. On the right, the loss plot tracks training loss in blue and validation loss in orange. Both consistently decrease, showing the model's error reduces as it learns. The validation loss staying lower than training loss hints at strong performance without overfitting. Overall, these plots demonstrate that the model was trained effectively. It achieved a higher validation accuracy while maintaining steadily decreasing loss, which suggests the model is neither underfitting nor overfitting.
So after this, uh, training the model. After training, we evaluated the model using metrics like accuracy confusion matrix and classification report. The confusion matrix provided insights into how uh, well the model predicted each network slice. We also uh, predicted each network slice. We also plotted ROC curve for each slice, which we'll see later. So this is the confusion matrix that we got.
So this is the confusion matrix showing the model's performance in predicting the three network slices URLLC, EMBB, and MMTC. For URLLC, 62 were correctly classified with only 2 misclassified as MMTC. For EMBB, performance is weaker with only one correct prediction and 11 misclassified as MMTC. For MMTC, the model performed well with 209 correct predictions and minimal errors. Overall, the metrics highlight strong performance for MMTC and URLCC, but suggest the model struggles with EMBB prediction, likely due to its smaller sample size.
After plotting the confusion matrix, there was generation of classification report, um, and which had a table formatted like precision, recall, F1 score, S score, and support for each of them. And then we also plotted the ROC curve for each slice to evaluate their respective performance in terms of true positives and false positives.
So this is the ROC curve, showcasing the model's ability to distinguish between the three network slices. URLC achieves an AOC of 0.99, indicating near perfect classification. MMTC follows closely with an AOC of 0.96, reflecting excellent predictive performance. EMBB has an AOC of 0.95, which is slightly lower but it still demonstrates strongly results. The closer the curve at the top left corner, the better the model performs. These values confirm our model is effective with URCC achieving the higher accuracy.
So after that, we had we plotted pairwise feature interactions uh, for each of the network slice, which look like this. The code is currently running. So this was the pair plot with KDE to make project more visually intuitive. We created these plots. Let's just take
This pair plot shows how different features are distributed across the three 5G network slices. Top diagonal shows individual feature distributions like latency, throughput, and signal strength for each slice. Off diagonal shows the relationship between pairs of features, highlighting how they correlate with each network. So The key observation are the EMBB has lower latency and higher throughput. URLLC shows higher latency, and MMTP typically has higher user density. This plot helps us understand the distinct characteristics and requirement of each network slice in 5G.
So at last, we made a simulated resource utilization heat map. So it is a simulated view of how resources are distributed among slices, providing insights into optimization.
The heat map shows the simulated utilization levels for each slice combination, represented by different shades of blue. The darker the blue, the higher the resolution utilization. The key observation from this heat map are the URLLC slice has a relatively low utilization of 0.35, indicating it has adequate resources available. The EMVV slice has a medium utilization of 0.81, suggesting it is using a significant portion of the available resources. The MMTC slice has the highest utilization of 0.86, implying it is consuming a higher portion of the resources.
Code explanation part.
So, in conclusion, this 5G techniques and machine learning techniques highlighting the potential for automated slice classification and resource optimization. We would like to extend our heartfelt gratitude to Bhupendra sir for his invaluable guidelines and support throughout this project. His insights and expertise were instrumental in helping us understand and implement the concept of 5G network slicing effectively. This project was part of our coursework in 5G communication and network, and we are grateful for the opportunity to delve into this cutting edge field. Thank you.